Hello, everybody. It's 12:01, so we're going to go ahead and get started. My name is John Levine. We're the Levine Electronics and Electric. We're manufacturers reps. We cover Georgia, Alabama, Florida, Tennessee, Mississippi, and Arkansas. We have two divisions, a control division, a power division. Please check out our website at l-3.com. Our philosophy is to get back to the industry, which is why we've been trying to hold these webinars almost every day. We also have 3 team members that are officers of IEEE and 3 other members that are actually in the IEEE Pulp and Paper Subcommittee. You can find recordings of these on our website under the recorded webinars. There's like 37 of them we've now got. We're actually known for being experts in transformers, arc flash, protection, and those areas. If you have any questions, you can type a question in the question box or chat box. We'll try to answer them at the end. We also have some handouts for this presentation that I saw, so you can download those during the presentation. We have 2 poll questions that we'll be asking at some point, and a survey question will come up after we finish. So there is a certificate of completion you'll get that you should have tomorrow by 5 o'clock. So with that, I'm going to turn it over to Mark Rogers, who's our presenter for today. Mark, it's all yours.
Well, I appreciate that, John. As John said, my name is Mark Rogers. I'm with ELSPEC North America. We've worked with L3 for many years. We're a manufacturer of power quality solutions, and we have a few different divisions, both on the metering side as well as the system solution side. And we also have engineering as well that can assist with analyzing power quality conditions within a facility and identifying potential opportunities for improvement. Today, what we wanted to do is talk a little bit about some of the changes in within the industry throughout recent decades and the impacts that power quality is being realized on different industrial and commercial operations throughout the U.S. and Mexico. We cover all of North America, but we don't just stop there. Oftentimes we fly to very remote parts of the world, working with the military, and have such clients like Fiji Water, and so we travel all over the place. And some of the things that we've noticed over the past several years is the significance of power quality and how that impacts operations is ever increasing, and has a lot to do with the integration of technology within operations and the advancement of that. Integration of things like more motor controls, whether that be VFDs or soft starts, integration of more nonlinear loads. The sensitivity of equipment has also, in some cases, has increased, which can have an impact on performance and reliability. And also, there's been increased demands on capacity. So in certain regions of the U.S. where there's a lot more constraints on the utility in order to maximize the efficiency of the power being supplied and utilized. So as many of you probably have taken notice over the past several years, the integration of all these things has seen an increase in harmonic levels, which can have an impact on equipment life as well as performance, increased current load demands, and probably of most significance in which we like to focus on is the impacts on the voltage throughout the networks and the variabilities being seen. You have to understand that as we all know, electricity is a closed loop system, so all aspects of that loop have an impact on the others.
Okay, so get back to the presentation. So as we were discussing before, with the increase of loads, increase of sensitivity of equipment, all of these things have an impact on equipment throughout the operation. And that's a lot of what I like to focus on. As my background as a reliability engineer, worked in the aerospace industry for several years on the F-22 program, the F-35, and really trying to determine root cause of not only failures, but weaknesses that we can help solidify and improve the reliability and resiliency of processes. And oftentimes this leads, the power quality has a significant contributing factor. And once improved upon, the secondary impacts, which are oftentimes lagging indicators, are quite significant. And being able to analyze those after the facts and the impacts that they're having can have a dramatic impact on an operation, their efficiencies, and their profitability. So some of the traditional electrical issues that are often observed out in the field is, nuisance tripping, whether that be of breakers or motor controls, VFDs, phantom PLC alarms, or that may impede on a process. Also, overheating of equipment, whether that be from an imbalance or elevated current draws, things of that nature, and how that impacts equipment asset life expectations, and even some small things that may not oftentimes be attributed to power quality, but can have a strong correlation. Quite frequently we see, we'll have clients call saying that they've had a brand new LED installation and they have frequent component failures, thinking that it's a manufacturing defect, when in actuality oftentimes it's a result of some of the dynamic nature of the network, whether that be from voltage variations or harmonics, and the impact on the components within those networks. And there's a myriad of different corrective measures that can be put in place, whether that be, oftentimes you might see a facility would adjust their transformer tap settings to increase their nominal voltage to ensure that whenever they have a large motor start, that it doesn't drop that voltage level to such a degree that it would impact other equipment on the network. Also, oftentimes they may put in some limiting factors within the PLC controls so that to impede on creating a condition which could trip things out. And you also have other solutions like inline harmonic filtration, isolation transformers, active harmonic filtration, and even traditional power factor correction solutions as well. But each of these all have secondary impacts that all need to be taken into consideration. Are you treating the symptom, or are you treating the cause? And oftentimes these can have negative aspects to it, not only from a financial perspective, but in a performance perspective as well. Reducing the efficiencies and performance of individual processes or systems or even motors. Increased heat, which is, most people without an electrical background understand heat. So how do we correlate these things together and look at how do we improve the overall environment and ensure operational uptime and productivity and efficiency ratings. So I guess from here, we'll just go ahead and start the first poll question. John, I don't know if there's anything I need to do on my end on this.
No, I've got the ball, hang on. I wasn't ready, shame on me. All right, there we go. We'll give you about a minute to answer this question. If you experienced any of these, check all that apply. Drives tripping, poor quality power factor, voltage sags, capacitor bank cell failure. That last one's a real issue, boy.
Yeah, we run across that quite frequently. And
Yeah.
this is a helpful poll question here too, because this can help focus on, we've got a myriad of different case studies, but we can help guide that and show what's relevant to some of the audiences attending.
I don't know if you're looking at the results, Mark, but looks like drives tripping and voltage sags are leading the pack.
Okay, good to know.
So you can't, you're not looking, you actually can see the results as they come in if you open up the poll box.
Oh, there they are. Okay, wonderful.
Isn't that cool? Yeah, you get to see the answers.
Boy, if I only had this back in college, right?
Yeah.
Well,
Uh,
good. So it looks like drives tripping and voltage sags due to motor starts.
the two biggies. Yep.
Two biggies. Well, good. Well, good.
Yeah, they got
Um,
66% of the votes. All right, I'm going to close it and let you have your presentation back. Time's up.
Wonderful.
Okay, we're back to your presentation.
Sure. Am I showing screen? There we go. Can we see the screen?
Yep.
Perfect. Well, good. That's good to know. So some of the traditional solutions, which include power factor correction, which is, these systems operate on an electromechanical contactor based, where it's the primary purpose is just to correct for the power factor, which is advantageous for utilities and in order to get rid of any associated penalties that may be ensued. But there's a lot of negative aspects that if the system isn't designed properly can have a negative impact. And this one right here, you can see that we had a traditional power factor correction system engaged, and then we turn the system off for a little over 5 minutes and then re-engage the system. And you can see that the functionality of that system will bring in a single group at a time, and usually with about a total correction time period of well over 2 minutes. So each stage is usually brought in every 20 to 30 seconds. But you can see the impact. There is a rise in voltage from the untreated condition, but oftentimes these fluctuations in between this time period cannot be accounted for just due to how it operates and functions. But also, if the system isn't tuned properly or designed to fit, the network conditions that are present, you can have some negative impacts on harmonics. So you can see here that their total harmonic distortion for voltage when the system engaged is about 5.6%, which is fairly significant. Whereas when it's disengaged, that's then reduced to 3.4%. And every single time these groups are brought in, you see these spikes in the harmonic distortion, and you can also see the transients being induced. Now, these transients not only are applicable there at the system, which can damage the internal components, as was stated by John previously on the poll question. This is quite frequently why traditional power factor correction systems are in constant need of maintenance, because these transients are going to propagate not only within the system, but also on the entire network, and can actually have an impact on systems and processes further downstream. But by doing that, those transients are going in and breaking down the insulation on those capacitors, because when that contactor hits, it's all three phases are engaged at the same time and at a random state, right? So it's going to induce that transient. So it's not uncommon to see walking through a facility, seeing power factor correction systems that are just locked out and tagged out, or nobody knows if they're really working or not. And most of the time they're partial at best. So the ELSPEC works on a different principle. And although it is our systems are power factor correction solutions, it's really a side effect of the main purpose and functionality of the equalizer system. Our system works on a principle of VVO, which is VAR voltage optimization, and it's based on this principle is based on the correlation between the voltage level and the reactive power demands of all of the equipment
downstream. So you can see right here, this is a 4160 volt motor, and you can see
Mark.
Yes.
You just went scratchy again. You were great for 15 minutes.
I haven't moved. Okay. Well, we're gonna double check.
You hear the audio playback, the video I record, you'll see what we're talking about.
Okay. Well, I'll also record this as a separate entity, and so it'll have perfect audio at that point. So I apologize for any technical issues that may be observed. But you can see in this graph right here, we've actually charted both the reactive power as well as the voltage. So you can see as the reactive power increases as a direct impact on the nominal voltage on the network. And in the lower graph, we've actually charted out the RMS voltage versus the total reactive power. And you can see the strong correlation here. And it's not only for medium voltage, this is for low voltage as well. This is an office building that you can see the elevators constantly being engaged and disengaged, and that having a direct correlation with the voltage as well. So what the equalizer system does is actually compensates for that in real time. And for those that are not as efficient or knowledgeable in the electrical world, I oftentimes provide the analogy and the similarities between a compressed air system and an electrical power system. Where in a compressed air system, you have two components of pressure and flow. The pressure is what's required for the equipment to properly operate and what it's designed for. And the flow is actually what provides the work. And similarly, in electrical supplies, you have your voltage and the current, which is direct correlation to pressure and flow. In as such, you have some inefficiencies and losses. So anytime you have a very large load that comes in that requires a lot of air pressure, it's going, or a lot of flow to continue the process, that has an immediate impact on the pressure on that entire system with a drop in pressure. And similarly, as we just saw there, the same holds true with voltage. When you have a large inrush of current demand, all of a sudden that will have can have a significant impact on the voltage levels. And you also, with a compressed air system, you have inefficiencies and flows, whether that be from system leaks or from turbulence and flow, which has a good correlation with the reactive power demands as well as the harmonics in the system. It's just resistance to the flow. So what we can do to actually improve upon that in a compressed air system, if you have wide variability in these pressure on the network pressure, then a facility might incorporate a demand expansion tank so that it can provide that instantaneous pressure, compensate for those large loads that are being brought in. And in essence, that's exactly what an equalizer system is. So an equalizer system can provide that instantaneous demand need for reactive power in such a way that it provides a stable pressure on that network throughout, stable voltage level. So as with a compressed air system, where although all of the components within that system may require a 90 psi pressure, oftentimes you may see it running at 100 or 110 psi because in order to account for those pressure fluctuations and not impact the process. Whereas if you're able to create a steady environment, now you can lower that the requirements on the compressed air system so that it can maintain that 90 psi and maintain its efficiency rate. So what the equalizer does is, in that same principle, our systems are in essence very similar to a traditional capacitor bank, but how it functions is much different. All of our systems are fully electronically switched, so we don't utilize electrical contactors. We measure and calculate the the network load demand in less than a quarter of a network cycle. And then the system actually waits for each phase, the voltage waveform on each phase to cross the zero threshold. And at that point, you bring in each of those phases. So in doing so, we're able to have total response time and bring in as many groups as necessary in typically less than one network cycle, and we can bring it all out in less than one network cycle. So it's virtually instantaneous load demand compensation, and with no moving parts, no transients. And this has a really significant impact on the voltage stabilization on the entire network. And what's interesting about that is the impacts of creating a very stable voltage network on equipment performance and production can be really quite significant, because instead of having a variable supply that each of the loads has to account for in order to either maintain steady torque or steady speed, now we've minimized that strain on the equipment and minimized the amount of current being needed to compensate, all leading to less heat, more stability, and more efficiency. And I'll show you some case studies here that actually shows the data, because obviously many of us here are engineers, so we want to actually seeing is believing, right? So at this point, we're going to try to play this quick little video, because oftentimes seeing it in action is gives a lot better understanding. One of the things I'll make of note here is this is actually the face of our controller, and they're going to go through different applications and uses. And this section up in the upper left is actually each of the groups being brought in. So if you have lights here, that's when a group is engaged, and when it is blank, that's when it's disengaged. We have both balanced and unbalanced systems. So in a balanced system, we treat all three legs equal in the sense of compensation. So we base the compensation on the average of the three legs, whereas an unbalanced system, we take each leg independently. So this is most commonly used in welding type applications, where you have vast differences between the phases on demands. So in seeing that, you'll notice that these three bars in those systems can actually operate independently. So just giving you a little bit of background on what you're looking at, but we'll go ahead and try to play this quickly and see how this goes.
ELSPEC is active in various industries using its equalizer, a real-time thyristor switched capacitor system. In plastic plants, molding machines are fed by a single transformer, resulting in fast changes in reactive energy demand and voltage fluctuation. The ELSPEC equalizer system compensates in real time any demand of reactive energy. The results? Voltage stabilization and power supply enhancement. During production of wire mesh, current consumption may reach thousands of amperes repeatedly. This mode of operation reduces the mesh quality and increases the flicker level beyond the permitted range. The ELSPEC equalizer system reduces the voltage drops and substantially improves the flicker level and production quality. ELSPEC has supplied the equalizer systems for most of the car manufacturers around the world. The equalizer system is mainly used in the welding shop, where the current consumption changes extremely fast due to a large number of welders. The equalizer compensates within a less than one cycle any demand of reactive energy, resulting in stable voltage. Thanks to the ELSPEC equalizer system, production quality has been improved, saving time and money in the quality control process. ELSPEC supplies the equalizer systems for many crane applications in seaports worldwide. In locations such as Santos Port in Brazil, the equalizer system was installed in a control room located on the top of the crane. When lifting a container, the consumption of power and reactive energy increases and the voltage drops. With the equalizer system in place, the voltage drop was eliminated and the lifting capacity was improved by 20 to 30%. A national water supply company chose ELSPEC to supply a motor startup solution for a large pumping facility. The facility included 4 motors of 11 kV, 3,500 HP each, connected through a transformer to the facility 22 kV supply. A motor starts up is demonstrated during a period of a few seconds. The EQFP equalizer controller connects all groups immediately and disconnected the group step by step at the end of the startup. The voltage drop at substation was improved from 10% to 2.4%. The current was reduced by 44% and the startup period from 4 seconds to 3 seconds.
ELSPEC, when power meets quality.
So as you can see, there's a variety of different use cases and benefits for various different types of applications. So what's interesting about the ability of the equalizer system to stabilize the voltage is, as you saw in this video, that it can actually replace the need of soft starts if it's not process required. So as with the water pumping station, you can see here, from a financially beneficial aspect in medium voltage, it's a fantastic opportunity where instead of having to install soft starts on each and every motor, you can have one system that can actually account for that. Seeing as that with a soft start in many applications, the only purpose is to minimize the impact on the network voltage of that motor start. With the equalizer system, it's accounting for that. So there's it can be utilized in place of that if necessary. And also, you know, with welding and how welding applications and the impact not only within the welding but also in neighboring production areas, being able to isolate and mitigate any of the impacts of different areas. So we have an engineering division that can look at specific use cases or specific issues that, or areas in which that you're trying to improve upon, whether that's unplanned downtime or VFD repair replacement costs, and minimizing that, extending the life of equipment out, and really determining the optimal solution. Much like what you saw in that video on the pump motor startups, you can see that we reduced the voltage sag from 10% to 2.4%. We could have eliminated that completely, but we oftentimes look for what's going to be the achieve the goals and have the best financial return to meet the objectives and really design a custom solution for that. On that note of customization, we design and build all of our products and can custom engineer it to be able to account for any specific situations, whether it be real estate limitations. As an example, we had one client who needed to put some systems on a specific network, but the only space available was actually underneath the MCC room, and that area only had a 5-foot clearance. So we were able to build a system that was 4 feet tall and wider in order to meet those requirements. Or, you know, need NEMA 4 explosion proof. We can get it, you know, if there's salt water or in a caustic environment, we can protect the internal components. So we can really customize to and design what's needed for the application. So, stop that. I guess we'll go ahead and we'll open this one question up very quickly, and then we'll actually get into some case studies to actually show some of the resulting impacts.
I was ready for you this time. We'll give everybody about a minute to vote. Or if you may want to pull up the questions and start looking at some of those so you'll be ready to answer them when you finish your presentation. We got some good questions out there.
I'm only seeing one.
I drag it, you can drag it to another part of your screen and then expand it. You probably got about 12 or 15 questions.
There we go. Just looking at it wrong. Why? Expand this. Okay.
Your sound came back good. We went scraggly for a while now. After you did that video, it came back great.
Oh,
All right,
good.
I'm going to close this. Basically, 25% of you said you do have voltage stability problems. All right. We're seeing your presentation again.
Okay.
That's your screen.
So what we'll do here is I'm going to go through, show you some information, or show you some.
You just went scratchy again.
Really, I haven't moved a single thing. Interesting. Okay, well, we will try this and see where this takes us. This just to kind of show you the capabilities in various different aspects. This was a textile plant. This one system was actually installed on their compressed air network, where it was comprised of about 12 or so large air compressors that would come in. And prior, when we were doing the baseline analysis, looking at what the profile looked like, they were, and we see this quite frequently, in especially in industrial applications, where they were running at full load, and when at full load, we were seeing about 495 volts on a 40-volt network. So after installation, we were actually able to tap that transformer down by one level. In that, the plant's objectives for this specific project was they really wanted to optimize their energy consumption and get the best efficiency that they could. So I was actually logged in and looking at their data while the maintenance manager was at the system, and we were looking at it with the system engaged under typical settings. You can see that the voltage was right about 478. We did some system testing here and then turned the system off for a while, and then during that time period, we actually went in and customized and kind of looked at the controller settings. Instead of telling the controller to base its compensation on the average of all three legs, we told it, okay, let's base the compensation on the average of these two top legs. So what that ended up doing is, you can see that when the system is disengaged, there's a fairly significant amount of current imbalance, which is not unheard of these days with, depending on the types of equipment and the processes in place. But you can see that once we actually tweak the settings a little bit, we raise the voltage even higher, just by a little bit, but we actually better balance the current loads. And in doing so, you can see on the active power how you can see a market improvement from when it was engaged versus disengaged. But then even by tweaking some of the settings, we could actually get that down a little bit further. There's some industries that we're very well known in, one of which being the automotive industry, metal stamping, plastics, extrusion, things of that nature. And the reason for that is just due to the volatility of the processes, lumber mills, injection molding, sawmills. So on this one is a metal stamp, and you can see metal stamping operation, their nominal voltage was about 460. And then when it was under load within the stamping process. You can see they're reaching about 420 volts. Whereas after we actually compensate, we've maintained this very, very tight bandwidth where the majority of the time it's only a 4-volt variation. It was all attributed to the reactive power demands of that load. And you can see here, this is a very good example of the impact on peak currents. So prior to the system being engaged, we're running about 3,700 amps, whereas after, with the system engaged, we're only running about 2,500 amps. Now this has a very large impact on equipment longevity because we're reducing the amount of heat that's being produced and transmitted to all the components, and heat leads to wear, obviously. This was some statistical analysis where we actually looked at where the voltage levels resided, both with the system engaged and the system disengaged. And you can see this wide region with the system disengaged in this 90 percentile zone here, ranging from about 448 to about 464. But when the system was engaged, the lowest value ever reached was actually the highest value it reached prior. But for a majority of the time, it resided within this 4-volt region, just maintaining a very steady network. And this is probably one of my favorite slides here because we've superimposed both the engaged and disengaged time periods. You can see that the top line here is with the system engaged. The bottom line for voltage is with the system disengaged. And you see as it goes, initiates the initial stamp, that voltage drop has a significant impact on the active power requirements of the system. So this purple line right here, you can see that as it is being engaged, it has a very jagged profile. And the reason for that is that the motor is constantly chasing this voltage drop. As your voltage varies, the torque to kilowatt ratio for all your motors are going to be impacted. So once we're able to raise that voltage level and maintain a very, very tight bandwidth, now all of a sudden you can see in this green line, it's just a smooth transition up. And there's actually a little bit of a leftward shift because the equipment is able to perform in a much better environment and power quality conditions. It's actually enabled it to perform its task in a much more efficient manner. And you can also see the difference in the differences in areas between the two lines is actually its kWh savings. So it's quite significant. This actually led to fairly significant impact on their production rate. So this is all process driven, right, and application specific, but in this case, you can see that we actually raised their production rate by a little over 9%, which is easy to see in this type of data. So we raised their voltage by about 3%, reduced their peak currents by about 28%, and increased their production rate by 9% with an energy savings of about 12%. So the capabilities and the impact of creating a stable environment can easily be seen in the operations and performance. Welding is another really good application for us. As I was saying before, we have unbalanced systems that can treat each individual phase separately. You can see here with the system disengaged versus engaged, we've raised the voltage levels by about 5. But whenever the welding processes are being initiated, you can see this peak current here of 1,800 amps. We've reduced that down to 1,100, and these voltage swings, instead of having a 20-volt voltage differential, now we're talking about 5 volts. So reducing the peak power, reducing the current, all of which actually had a remarkable impact on that production area's performance. So they were able to reduce their rework requirements because we were able to stabilize that voltage and stabilize the current. It made the qualities of the weld much better. And also because we're reducing that current and reducing the amount of heat required for that process,
we extended the life of those welding tips by over 33%. So quite significant. Also, lumber mill, we actually had this project that was independently measured and verified through an engineering consulting firm for a utility incentive program that the client wanted to be involved with. And we did extensive regression analysis looking at every single possible variable, from diameter of the wood to moisture content, atmospheric conditions, you name it. And you can see that even for their static processes, which is very easy to show because the kiln is a steady state process that never really changes and runs 360 days out of the year. They saw about a 6% improvement on kW reduction and kWh consumption. And also on their sawmill process, they saw over 11% improvement. So the more dynamic the process is, oftentimes the better the improvements and the results. We even had benefits in areas that weren't treated, because when the sawmill was in production, they were averaging about 470 volts on a 480 volt network. But when the process was, when the sawmill was not in production, they were running about 515. So here, because it's the easiest way to illustrate this, this is actually the kiln. So it's a very steady state process, but you can tell whenever the sawmill was engaged versus disengaged, has a significant impact on the voltage. And you can even see that and how it's impacts the current draw on this network as well. You can see after the fact, now after implementation of the equalizer systems throughout the facility, we were able to adjust all of the transformers throughout the facility by 3 levels, reducing their secondary supply level by about 7.5%, and then maintaining that. So in looking at some of the power profiles, on this static process, they were already running at a 0.90 power factor. So now we've actually increased this. This was actually our ActiveR system, so that has a little bit slower of a response time and is designed for very steady state processes, which this is obviously applicable to. You look at the active power going from 985 kilowatt average to a 935, and their apparent power going from 1085 to 945. So we're basically collapsing this power triangle and then keeping it at a steady state. But what was most impactful to the operation was actually the improvement to their overall operation. That they had one electrician per shift whose primary purpose was to go around resetting breakers and resetting VFDs. So they'd have about 10 to 15 nuisance trips per shift. After we stabilized that voltage and got that voltage in its optimal region, now all of a sudden those were virtually eliminated. They also had phantom PLC alarms that they could never explain. As soon as the network was stabilized, all that went away. They had numerous VFD failures every single week. All of a sudden, that was drastically reduced. Once, obviously, there's going to be some pre-existing conditions, but you can see over time that it has a very marked impact on their VFD repair replacement costs. And all of this leads to more uptime, better KPI metrics. This one facility was all of the facilities within this organization were ranked every single month on cost per 1,000 footboards, and this one facility was always dead last for years, and the very next month after we implemented this, they were in the top 3. So it was pretty impressive. Similarly, we've in a large refinery, we had some very impressive results in this as well. Looking at this is a low voltage condition with the system disengaged, we raised the voltage quite considerably. You can see the significant impact on the current. But was most impressive is that after a couple of months, as soon as we turned the systems on and we stayed on site and we're doing some analysis, we saw about a 10% production rate improvement. And it was primarily due to how the process was controlled. Some of these had current limiting inputs. So as soon as we were able to lower that current, it was actually the process automatically increased rate to match, the current limit. But they were also, after about 2 months, we started noticing that their production rate just kept increasing and increasing. And now they're over 25% production rate improvement, and couldn't figure out exactly why. When we started going and talking to people at the facility, we finally got in charge of the manager who's in charge of all the process controls, and he said, well, he'd been playing around with things and realized that he could just remove all limits within the control logics because they weren't applicable anymore. And he was able to just let equipment run flat out as it was designed. All of this had really significant impacts, and it's become their most profitable plant within the organization. But even more so is that we started looking at it from a long-term basis and looking at what were their overall operational costs and their VFD repair and replacement costs, their motor repair and replacement costs, and looking at it from a long term over several years, and started to realize that their VFD repair and replacement costs had gone down by over 60%. Their motor repair and replacement costs had gone down over 50%. And the only market change was the implementation and the stabilization of the network. So it can be a lot of things that aren't naturally attributed to power quality. You can also oftentimes see a very significant improvement once you provide a stable network. We also do medium voltage applications as well. We design the system based either on a 600 volt or 690 volt platform, and then utilize a step-up transformer to bring it up to whatever voltage is necessary, whether that's 4160 or we've actually done work for utilities and done it at the substation level and regional distribution to stabilize the network from wide customer and client load demand variations. You can see here, this is actually a large food processing facility throughout the US. On their 4160 side, they have 16 large ammonia compressors. And when you zoom in to an area like this, you actually see that each one of these was actually 4 independent starts and had a fairly significant impact on voltage, dropping it down to below 4,000 volts. Initially, the customer had asked us to set the target power factor at 87. He was an old utility guy, and that was, that made sense, and it's kind of the target he'd always aimed for. So initially we set it to that and took some data, and then I told our guys, like, go ahead and set it to 98, leave it overnight, come back, and let's just capture some data, because we were leaving capabilities on the table here. So you can see here that although this voltage drop occurred, this time period right here is actually less than 2 cycles. So from an equipment perspective, it's not even realized. So then we actually compared, we had multiple meters, one on the utility side of the 13.8, as well as downstream. And you can see that we've actually compared the previous baseline measurement upstream to once the system was actually engaged. You can see that even had quite a significant impact on the 13.8 side, which is being seen throughout the operation, even on the low voltage side of the facility. When we set it to target power factor 98, you can see we even shortened this and added even greater stability to the network. So it's very, very significant impact. It can also work. We're actually the only solution when it comes to either cogen or island networks, local generator power supply. Most manufacturers clearly state that any power factor correction system cannot be on the same network, with a caveat on our system. So we've had long-standing experiences with CAT,
with Caterpillar, with Cummins, because our system and how it operates, it's actually the only system that can actually effectively work on a generator network. You can kind of see in a generator, oftentimes when an event occurs, like a motor start or something of that nature, they have integrated AVRs or automatic voltage regulators. But as you can see, in many instances, in this case, this is a failed motor start because due to the lack of reactive power availability from the generator, it can actually impede the startup on that process. And not only that, but you can also see on this AVR, oftentimes by the time the AVR responds, the event is oftentimes over. So you will get this overshoot and create an overvoltage situation, which can also trip things out. Basically, what the equalizer does is it takes all the load off of the AVR. You can actually hear it in many installations where as soon as you actually engage the equalizer, we've heard as much as an 18 decibel drop because it takes all the load and the variability of the load away from that generator and just allows the generator to do what it needs to do. This has a significant impact on the overall reliability and maintenance requirements of the generators, where we've had several instances where in the Caribbean or in Fiji, where they were having ongoing issues with their generators and keeping them online. But as soon as we stabilize that network, all of those issues just magically disappeared. You can see here, this is a steady state power curve, a reactive power curve, which is often quite common in the generator world. And you can see that the generator optimally needs to operate in this acceptable steady state region. Prior to the equalizer being engaged, we really couldn't keep it within that region during those motor starts. So we were constantly coming over into these regions where it's actually generating additional heat and wear within the generator itself. Whereas once we actually engaged the equalizer, it could never get outside of that zone. This also can have quite significant impact on fuel consumption in this regard. So as with Fiji Water, they have at that one facility, I think they have about 38 systems. Whenever they add a new production line, they don't add any gear unless it has an equalizer with it, because they've had such an improvement in reduction of fuel cost and reliability that it has become the standard. We have several others, but I guess maybe we can go to some questions first, and maybe that might assist trying to see if I can, for some reason I can't.
Can you open the questions and see them?
Yeah, it's the window that lists the questions is very small. I can't seem to expand.
You can widen the screen, that section.
Yeah, that's what I'm trying to do, but it's, well, I'm just not having good luck today, am I? You mind helping me out, John, a little bit? Oh, there we go. Now it moved. I got it. Okay. Scratchy's still bad. When you say replace soft start, does that mean the contractors, the contactors as well? No. It can replace the need of a soft start. So instead of, unless the process requires a soft start, just due to the nature of the system and how it functions. Otherwise, the motor can just be utilized as a cross-line starter or direct on-line motor start, because
Mark, minimize your PowerPoint a second. I want to see if that helps your voice quality. Now say something.
Something. Is that better?
That didn't help. Okay.
No. Okay. So instead of requiring the soft start to minimize that voltage drop, the equalizer does it for it. So now that soft start in that specific application wouldn't be required because the equalizer is providing the voltage stabilization versus the soft start minimizing that voltage drop impact. Can you do a load flow analysis on startup and steady state via ETAP, easy power, etc., before you quote a solution?
Read the question. Let me read it because maybe my quality's better. Can you do load flow analysis on startup and steady state via ETAP, easy power, etc., before you quote a solution?
That's a great question. So yes, that is possible, and it's about getting the model accurate. So we've got several different tools that we can utilize, but basically, if we have some measurements to see exactly what the load profile looks like during startup conditions, and if we have some other information, one-line information, so that we can build a basic model of a model within a simulation program, then we can actually add the new component to show the voltage stabilization and see what the resulting impacts would be. So yes, that can be done, and we have done it. Let's see. We were experiencing huge voltage sags when a 1,000 horsepower water pump starts. Can you determine which option is better between choosing an equalizer or a soft start? Sure. So one of the advantages, if a soft start isn't required to actually, just due to the nature of the process, then the equalizer is oftentimes a much more advantageous solution implementation, because a soft start only engages during the start, right? So then after the fact, it's bypassed, right? So with the equalizer, it's not only engaged in providing compensation during that startup, but also during nominal operation. So any fluctuation in load or in demand, it's providing that constant voltage continuously versus only being utilized during a startup condition. And oftentimes for a medium voltage application, it's much more cost effective for an equalizer in many cases to treat the entire network versus just having a single soft start on every single motor. Now you can have one equalizer system that can be compensating that entire circuit and all the loads within it. Is this equipment a capacitor bank? Yes, in essence. So this is a capacitor bank, and it is, as I said before, it is a power factor correction system in essence, but how it functions when you compare it to a traditional capacitor bank, that's where the differences and the functionality differ. So this does provide reactive power, but how it functions and being able to do that instantaneously, we can go from 0 kVAR to 100 megaVAR in less than a network cycle, and then we can take it all out in less than a network cycle. And the impact that has, not only on that piece of equipment, but all the equipment within that network is quite significant. And it also has a really advantageous impact for utilities as well. Oftentimes we partner with utilities throughout the country. They utilize our meters for diagnostic purposes. They also have brought us and got us engaged when clients are having issues that they can't determine, where it's coming from or what the issue is, and we can come in, determine exactly what's going on, and provide a resolution in a very timely manner. Are there any stages or steps, or just one large stage that is varied? No, so there are stages, and it depends on the size of the system, but each stage will have a specific value in it. And typically, our smallest steps are generally between 33, 38 kVAR, or more commonly, for larger systems, we utilize the smaller steps of 66 and 76 kVAR. So we can get that's a pretty darn tight resolution where it can really account and create a unity power factor constantly and continuously.
Mark, the person that just asked that question is a paper mill customer. And because you're switching electronically versus contactors, don't you dramatically extend the life of the capacitors?
Absolutely. So
Less issues with
one of the real big advantages of our system is that our system has, other than a cooling fan, our system has no moving parts whatsoever. So because it's all electronically switched, and each phase is brought in that zero, when the voltage is crossing that zero threshold, there's no transients. And we also have, we manufacture all of our own inductors, all solid core. So we absorb those harmonics, we stabilize the voltage, all completely transient free. So due to that fact, these things are incredibly robust and resilient. We had a customer call us last year and said, I just took over as plant maintenance supervisor for this large Nestle plant. He said, I've been here for about 6 months, trying to get my feet on the, stable on the ground. He goes, I'm walking around, I see we've got 18 of your systems, and nobody really knows what they are. Nobody knows if they're really working. They've been here for 15 years. Can you send somebody over here and take a look at them? And when we got there, looking at them, doing some PM services on them, they were still running the same that they were when we installed them 15 years prior. So due to that, the capability of it, having complete transient free operation, they're incredibly robust and resilient. Oftentimes we've had clients that have existing cat bank systems that they're constantly doing maintenance on, and we're able to cost justify it with replacing the system, because their annual maintenance on the system that they had was about the same cost as putting a new system in, that they won't have those issues with again. Does the system have an option for maintenance bypass switch? Yes. So we have manual mode, which will disengage everything. I think that's the question you're asking. But the maintenance for these types of application is minimal. The system actually performs self-diagnostics constantly. Not only that, an interesting thing with integration. Oh, let me share. Am I still sharing? Yep, there we go. So with our software, in our systems, we can integrate our continuous waveform recording meters as well. So our metering division, all of our meters are continuous waveform recordings. So you don't set any parameters or any triggers or any events. It just records all power quality parameters all the time. But another interesting aspect to this is you can actually access the controller remotely. So where was this? Here's an example. It's one that I set up. It's not actually, I'm not actually live connected to it right now, but if this was connected, we would actually see exactly what's on the controller and remotely, and we can actually change parameters. We can view system logs, adds another layer of remote diagnostics capabilities on it. So, because oftentimes, as we all know, people don't oftentimes go and have the time to go check around and ensure that things are running. They just oftentimes just expecting it to.
Mark, we're running out of time. Why don't you see if there's any other questions there you want to ask? If not, we can contact these people directly.
Sure. So as John said, if anybody have any additional questions or comments? So at 40 volt was the largest typical stage kVAR rating. Typically our largest groups are 152 kVAR. So another thing that we oftentimes seeing in out in the industry is people will put large stages, especially like on medium voltage, where they may be bringing in a single stage, maybe 2 megavar or 1 megavar. That has a huge impact on the voltage levels, and when those things come in and out, that can actually trip things off on its own. So in order to achieve the voltage stabilization of effectively, you need to have a tighter resolution. So typically our systems have the smallest step, as I said before, is generally either 33, 38 kVAR or 66, 76 kVAR, with the larger groups being 152. We even have other systems with a large step of 264. But we can customize that, you know, depending on what's necessary and what's required. Can you do 3 megavar at 5 kV? Yes, absolutely. We've got a system that we're installing right now up in Minneapolis area. It's about 3. It's almost those exact specs. So yeah, we can custom design anything. As I said before, on anything over 600 volts, we utilize a system rated at 600 volts or 690 volts, and then utilize a step-up transformer to bring it up to whatever is required.
Great.
Stepped up. Yep, it does need to be stepped up. The direct connect on for electronic switching on that medium voltage is a much different beast. So we've actually designed and built direct connect at 4160 before, or at high voltage, other medium voltage levels, but it's actually what we've come to find is the cost associated with that versus doing it on the low voltage side and stepping it up is about the same, if not a little bit higher. And doing it at the low voltage actually allows for easier maintainability. You don't have, you're not required to have certifications to get in there and do any maintenance or anything of that nature. So it can be, there's a lot of other benefits to the client that taken into consideration.
Mark, thank you very much for doing this presentation. For the questions we didn't get answered, give me a call, or Mark and I can reach out to you, and we can discuss some of your specific applications, because it's definitely, we got a lot of questions here that we weren't able to address. Everybody, thank you for your time, and be safe out there. Thanks, Mark.
Thank you.
Bye-bye.